Let us now discuss different modes of operations. Initially, these were developed for DES, but it can be used for other block ciphers. Now, why we need this? We have observed that DES encrypts a plain text of size 64 bits and uses a key of size 56 bits. Now here I want to recall that when we give the key, initial key, this key 56 bit, but it comes in a packet of 64 bits. And 8 position in that key, 8 position, 16 position. So those positions are parity check bits. So when we consider the key in generating the 16 round keys, K1, K2, K16, this is 16 round DES. So in while generating the applying the key scheduling algorithm, the initial key is taken to be only 56 bit. Those parity check positions are not considered. Now, if you have a very long plain text, we divide those plain text into blocks of size 64 bit. For DES is 64 bit, so that we can apply this encryption scheme. So there are several ways we can encrypt a long plain text. These are the different modes. ECB, there are four main modes: electronic codebook mode, electronic codebook mode (ECB), CBC is ciphertext blockchaining mode, OFB output feedback mode, and CFB ciphertext feedback mode. So these modes, they differ in which way we generate the from plain text, how we generate the ciphertext, how we apply the DES or any other block cipher using the key. Okay, so they differ. Each of them has their own advantages and disadvantages. We are going to discuss those. Now, first ECB mode. ECB mode is electronic codebook mode. So this is very simple. The name use of block cipher. So you have a very long plain text and you divide it into blocks of same size. So blocks of size, X1 is a block of size L, X2 is another block of size L, like that. So I have M blocks, suppose. And each of these blocks, plain text blocks, are passed through the encryption box. So this is actually DES algorithm. We apply DES algorithm using the key, same key, and X1 is encrypted to Y1, X2 is encrypted to Y2, X3 is encrypted to Y3, XM is encrypted to YM. So your from this plain text blocks you get the ciphertext blocks Y1, Y2, YM. Simply applying your encryption algorithm. It can be your block cipher. It can be DES, it can be AES, or it can be any other block cipher. SPN, it can be SPN also. Okay, so the weakness is if you use this mode, this way you encrypt, then identical plain text blocks in identical ciphertext blocks. So X1, X3, X7, if all these blocks are same, then Y1, Y3, Y7, these ciphertext blocks will also be same. So this gives a leakage. This gives leakage. So plain text is not mixed properly. So from ciphertext you can infer some information about the plain text blocks. Okay, so specifically we have two things to remember while designing a block cipher. One is confusion, another is diffusion. What is confusion? Confusion means what we want the ciphertext and the relationship between the ciphertext and the key means there should be no clue among the relationship between key and ciphertext. This is what we call confusion. We make this process of generating yi's so that we don't get any clue about any clue between the relationship, any clue among the relationship between this key and the ciphertext. This is confusion, and for that purpose we use the substitution ciphers. We use substitution box, S box. Another thing is called diffusion, where we want to hide the structure of the plain text. Means plain text ciphertext relationship. We want to hide the plain text ciphertext relationship. So that is called diffusion, and for that we use shuffling or permutation. Okay. So for confusion we use substitution, and for diffusion we use permutation. And we want these things, this mixing as complex as possible, so that ciphertext plain text relationship is hidden. But in ECP mode, if you use the ECP mode, then you can see this type of leakage you can get about from the ciphertext. You can get this type of leakage about your plain text. And another thing is, unless provided your plain text blocks are chosen from a low entropy plain text space. Okay, so for example, plain text consists of entirely zeros or entirely ones. Okay, plain text consists of entirely zeros, entirely ones. So in that case, all the zeros will map to the same blocks. So there is no, so you can infer this thing. This is encryption of either 0 or 1. So information leakage happens. I have one example. I have one example. Say this picture. See this picture. This is a black and white picture. This is a black and white picture. And any picture, any image, you can get corresponding to any image. You can get binary string. This is pixel values. So say white part corresponds to white part corresponds to 1, and this black part corresponds to 0. So if you use ECP mode to encrypt this, then this whole thing is divided into blocks. This pixel, this is a very long plain text, and you divide it into blocks of fixed length. Then when you apply the ECP mode, electronic code book mode, then this white part, all the white parts map to the same value. The ciphertext string remains same. So what you get, if you encrypt this using ECP mode, then you get this type of picture. So you get an impression, means what actually was sent. You get that information is leaked to the ciphertext. So it is not the confusion it is not confusion. This is the shuffling. This diffusion is not properly done in this case. Diffusion is not done properly. Okay, here diffusion is not done properly. Okay, so you get information. You get a clue about the relationship between plain text and ciphertext. So this type of thing we don't want. ECP mode is having this problem. Next one is, but another advantage is, so this is disadvantage, this is disadvantage, but another advantage is that this x1, from x1 you are generating y1, x2 you are generating y2, these are all independently generated. There is no correlation, but the problem is this type of thing, this weakness. Okay. So you can make it can be parallelized, but this type of problem remains. So this is ECP mode, electronic code book mode. The next one is ciphertext block chaining mode. Ciphertext block chaining mode or CBC mode. So here what we do, so each ciphertext block yi is XORed with the next plaintext block xi plus 1 before encrypting with the key k. So while encrypting, before encrypting, your previous ciphertext block is XORed with the current ciphertext plain text block. So initially your Y0 is IV, so you XOR IV. IV means initial vector. Initial vector with initial vector you XOR the last plain text block, and then you pass this resulting value through the encryption box. Encrypted. You get Y1. Then this Y1 is XORed with the next block, plain text block, and then passes through the encryption box. This way we generate. So your ciphertext essentially consisting of this Y1, Y2, Y3 like that. So each ciphertext block is XORed with the next plain text block. This way, each ciphertext block is encrypted with the next plain text box before encrypting. After that, you encrypt and get the next get the ciphertext block. Then this ciphertext block is XORed with xi+1 next plain text block, and then encrypted, passes through the encryption box. So pictorially, it works in this way. Your initial Y0 is initial vector IV, and it is XORed with X1, first plain text box, second plain text box. Here you have all the plain text box, and it is XORed with X1, and you get XORed with X1, and then passes through the encryption box. You get Y1. Then this Y1 is XORed with X2. You get encrypted. You get Y2 like that. Okay, so this way you generate. And decryption is simply so decryption means from this string, from this you have to get, so you know your ciphertext, how to get your plain text X1. So you have to first decrypt it. You have to first decrypt your Y. You have your Y0 at hand, and the ciphertext Y1, Y2, Y3, you all have this. You have all these ciphertext. Y1, Y2, Y3 you have. So Y1 you first pass it through the decryption box. If you pass it through the decryption box, you decrypt it, you will get Y0 XOR X1. So with Y0, if you XOR with Y0, this Y0 and Y0 nullified, and you get X1. You get X1. Okay. So first you decrypt Y1 XOR with the initial value, you get X1. Then next Y2, next ciphertext block, you decrypt, and then XOR with Y1, XOR with Y1. Okay, XOR with Y1, you get X2. So for the second iteration, it is Y2 equal to EK of Y1 X2. So to get X2, you have to first decrypt it. That means decryption of Y2, and then you XOR it with this value Y1. So this way it goes. This is your CBC mode. This is your CBC mode. Blockchaining mode. Okay, cipher blockchaining mode. So encryption, decryption done in this way. Decryption is simply, it is shown here. You first decrypt. If you decrypt it, you get Y0 XOR X1. Then you XOR with Y0 this part. So XOR with Y0, this Y0 and Y0 nullifies, you get X1. Similarly, other values you can recover X2, X3, X4. So this is useful for authentication purpose. Authentication purpose means to produce a MAC, message authentication code. What is the message authentication code? Means you have authentication and data integrity. Means you are sending your plain text is x1 x2 xn. X1 x2 xn. Suppose you send x1 x2 xn together with the last value y1 you generate, then y2 you generate, ultimately last value ym you generate. So with this plain text x1 x2 xm, you also send this last ym, and that ym we call MAC, message authentication code. So you can detect you can detect whether your given plain text is altered somewhere. Data integrity is preserved or not. If some xi is altered, then you can check that. How means you have your initial y0. You can simply recalculate ym. You can recalculate ym. If somewhere this xi value differ, then that last ym value will be altered, because every time this y2 depends on y1, y3 depends on y2, so ym depends on y all the previous values, and similarly all the previous all x1 x2 xn. So if some xi is changed, then automatically last yi value that we are sending as a MAC, message authentication code, that also changes. So you can check whether your given data x1, x2, xn that you are sending along with the code, MAC value, that ym, whether this message is somewhere altered or not. Okay, so you recalculate the MAC value, that ym, in this way, applying this algorithm, and check whether that is equal to the received MAC value ym or not. If not, then the data somewhere has been changed. Okay, so you can detect whether your data integrity is preserved or not. So this is called data authentication, useful for authenticating authentication. So we can use this algorithm, this encryption algorithm, to produce a MAC, message authentication code. So this is what we have written here. If xi is changed in CBC mode, then yi and subsequent ciphertext blocks will be affected. Okay, so if xi changes, that means x1 changes, then all the subsequent, it is y1 changes as well as y2, y3, all y values also changes. So if you send plain text x1, x2, xn together with MAC value, the last ym value, then it provides a way to check integrity of your data, whether plain text is altered or not. You can check that. So it essentially uses for authentication purpose. It is not used for secrecy, for provide privacy. Okay, for provide privacy. So plain text, we are sending plain text. We are sending plain text. So this way, if you use this, then it does not provide privacy. It uses for authentication, data integrity purpose, authentication. Okay, now OFB mode. OFB mode is output feedback mode. So what we do, we from the given key, we generate a key stream. Okay, so key stream is generated. This is essentially it works as a stream cipher. I'll discuss stream cipher. So stream cipher we do in this way. We from the given key we generate a key stream, and each plain text bit is encrypted using this key stream. So this is what we do in stream cipher. Now OAP mode it operates as a synchronous stream cipher. Synchronous means your key does not depend on this key stream from this key you are generating key stream. It does not depend on the ciphertext or plain text or both. It depends only on key. From the key you generate the key stream. In asynchronous stream cipher, what we do, from the key we generate the key stream, and this key stream while generating does not only use key k, it also uses plain text or ciphertext or both. Okay, so that is asynchronous. Now OFB mode, how it operates, we have an initial vector, and given key, we generate a key stream in this way. So suppose K0 is IP, it is given. Okay. Now K1 we generate, how? We encrypt K0, we generate K1. Then encrypt K1, we generate K2. So while generating the key stream, we use the block cipher. We use block cipher to generate the key stream. Using the same key K, this given initial key K, we generate the key stream in this way. So this initial vector is given, and you generate the key string in this way using the block cipher. And encryption is simple, just XORing. Your plain text is x1, x2, xm, say L bit strings. X1 is L bit, x2 is L bit strings, xm is L bit string, and then these KIs are also M bit string. It should be these KIs are L bit strings. So KI and XI are XOR YI produced. Okay. Now for decryption also is a same encryption function can be used. So for decryption, to the decryptor, this K is available, and also the initial vector is also available. So the same way the decryptor can generate the key stream. This key stream can generate, and the ciphertext is available to him. He simply XOR KI with YI and get back XI. So if you XOR KI with YI, KI is XOR 2 times here, so XI you get. Nullifies and XI you get. So all this is XOR, so modulo 2 operation. So KI coming 2 times, that means it nullifies and you get XI. Okay, so for decryption and encryption, for both encryption and decryption, same EK is used. Decryption and encryption algorithm, encryption function is used. We don't use the decryption algorithm here. In the previous two modes, you can see that this CFB with the CBC mode. In CBC mode, we have used encryption algorithm here and decryption algorithm, both we have used. And in ECB mode also, while you encrypt, you use encryption algorithm. While you decrypt from YI, you want to recover XI, you use the decryption algorithm. So ECB and CBC mode uses both encryption and decryption algorithm on the underlying block cipher. But here in OFP mode, for both encryption and decryption, we use only EK, the encryption algorithm. Okay, this encryption algorithm. And why we call it stream cipher, I will introduce. Okay, synchronous stream cipher. Stream cipher means essentially from key you generate the key stream. So this is bit strings. These are bit strings. K1 is 1 bit, K2 is 1 bit, K3 is 1 bit, like that. And plain text also X1, X2, these are bitwise. Okay, bitwise. And then ciphertext generated for stream cipher, for this particular OFP mode, ciphertext is generated using just XORing X1 with K1, X2 with K2, X3 with K3, like that. But for general stream cipher, what we do, this YI is generated using encrypting X1 using KI. So Y1 is encryption of X1 using K1, Y2 is encryption of X2 using K2, Y3 is encryption of X3 using K3, like that. I will discuss those things. So that encryption here is simply XI XOR KI, the XOR function we are using. The encryption is simply XI XOR KI. So this is your output feedback mode. Another mode is CFB mode. This is ciphertext feedback mode. So this was output feedback mode. Output is feedback. Output feedback mode. And this is ciphertext feedback mode. As I said, this is essentially, this operates as asynchronous stream cipher. Means your key stream, when you generate the key stream from the given key, this key stream generation depends not only on K, it also uses plain text or ciphertext or both. In this case, here it uses key as well as, while generating the key stream, it uses key as well as the ciphertext. So that is why it is asynchronous. It works as asynchronous stream cipher. So it also uses initial vector. Initial vector is IV is given. It is say y0, and then you encrypt y0, you get k1, encrypt y2 like that. yi minus 1 you encrypt, you get ki. Y0 is this, Y0 is, so from ciphertext you generate the key stream using the say initial key. So your CFD mode, key stream, these key streams are generated using the ciphertext, previous ciphertext. Initial ciphertext, initial Y0 is IP, and then keep on encrypting this. So Y0 you encrypt, Y0 you encrypt, you get K1. That K1 you XOR with X1, you get Y1. That Y1 again you encrypt to get K2. And K2 and X2 you XOR, you get Y2. Y2, and whenever you get Y2, you again encrypt it, you get K3. Then K3 and X3 you XOR. Okay, so this is pictorially it is depicted here. The picture is depicted here. Y0 is your initial IV encryption process. You pass it through the encryption box. Your block cipher is generated here. Block cipher is generated here. The ciphertext, this is your block cipher, and ciphertext is generated here. That ciphertext is essentially your key stream, next key stream K1 is XORed with X1, you produce Y1. Y1 again you encrypt, XOR with X2, you get Y2, like that. Decryption also, from the key stream you generate your means you have your Y0 at hand, you encrypt it, you get K1. When you get K1, you XOR with Y1. Your ciphertext is, when you decrypt it, you have the ciphertext Y1, Y2, Yn. So Y1 you XOR with K1 that you generate using encrypting the IP. So you get X1. Then this Y1 you again encrypt, you get K2, and you XOR with Y2, you get X2. Then Y2 you again encrypt to get K3, XOR it with Y3, you get X3, like that. Okay, so here also in CFP mode also we use for encryption and decryption we use the same function, same encryption function. No, the decryption function is not used, encryption function is used. Every time encryption function. And mind that if you compare this key stream, when generating the key stream, we use the block cipher using the initial key. But here, this block cipher, through this block cipher, we encrypt, using this block cipher, we encrypt the previous ciphertext block. And while generating the key stream here, using the same initial key, we encrypt the previous key stream bit to generate the next key stream bit. Okay, so this is EK KI minus 1, that is your KI, and here EK YI minus 1, that is your KI. Initial vector is taken to be Y0, and their initial vector is taken to be your K0. Okay, this is asynchronous. This is synchronous because it does not depend on this key generation. This key stream generation does not depend on the plain text or ciphertext. It depends. It is derived using the key. But here, this one CFT mode, ciphertext feedback mode. Ciphertext feedback mode. It is using the ciphertext. That is why it is called ciphertext feedback mode. This ciphertext, this ciphertext is feedback. Whatever ciphertext encrypting, whatever ciphertext you get, it is feedback here to get the key stream. Then XOR again, it is fed to the encryption algorithm and generate. This is why it is called ciphertext feedback mode. Okay, and this one is output feedback mode. Okay, now another mode, this is very popular mode and this is very efficient. This is called counter mode, CTR mode. CTR mode. This is similar to output feedback mode. But the key stream generation is different. Plain text block length is block length is x. I have taken x here. Plain text block length is x. Okay, and in counter mode, what we do, we construct a sequence of bit strings of length m each. Okay, m each. T1, T2, Tm. We generate this sequence of bit strings. T1 is a bit string of length m. T2 is a bit string of length m. So sequence of bit string, how we generate using a counter. This counter may be 0 or it can be the initial value in the register. Okay, so Ti, we generate Ti to be CTR, the counter value, current counter value minus I plus 1 modulo 2 to the power m. Modulo 2 to the power m. So when I starts from 1. So T1, if you put T1, it is essentially counter value. Modulo 2 to the power m means, so we say that it is a sequence. This is a bit string. So we have to take the binary representation of that. Modulo 2 to the power m. So length should be m. Length should be binary representation. So we just think it as binary. This is integer value, but when you convert it into binary, its length is m. So m length string. Okay, so I think this plain text block length, plain text block length is x. Okay, fine, no problem. Okay, now plain text x1, x2, and cipher text. How we generate cipher text? We so our key stream is essentially, these are the key stream, and these are T1, T2, T3, these are the key stream. Ti is CTR minus I plus 1. It does not depend, Ti does not depend on the previous T values or any other T values. Simply independently these are generated depending on current value of CTR. Okay, so Y1 is X1 XOR encryption of T1. So your key stream is T1, T2, Tm, those are generated in this way. This is the difference between the counter CTR mode and OFD mode. So in OFD mode, here in OFD mode, we generate a key stream in this way. Ki is encryption of Ki minus 1 using the key K. The block is Ki. To generate Ki, we pass the previous key stream bit Ki minus 1 to the block cipher, and we get Ki. So encryption of Ki minus 1, and here this key stream Ki, this is essentially, you can say in OFD mode, this is Xi XOR Ki, this Ki, but here this is Xi XOR this Ki is here, it is Ek of Ti. Then Ti is this Ki minus 1 depends on Ki minus 2, Ki minus previous Ki values. Okay, but here these Ti's are independently generated. Can be computed, this EKTI can be computed independently of any other key stream element. Independently. Well, EKTI does not depend on prior plain text or prior EKTI minus 1. So this is why this makes this counter mode efficiently implementable in software or hardware by exploiting opportunities for parallelism. Okay, lots of parallelism you can incorporate, because this Ti is never depends on the previous plain text or previous cipher text or previous key stream. It is independent of Ti is independent of T1, T2, Ti minus 1. So independent, there's lots of there's scope of applying parallelism. So this permits very efficient implementation. there are other different types of modes. Counter mode together with CBC mode. CBC mode is used for authentication. Already I have mentioned. Counter mode. This can be used for privacy purpose. So this essentially this hides the structure of the plain text. This hides this way. If you encrypt, this hides the structure of the plain text because these TIs are independently generated and independently generated. So XIs are mixed properly. So from YI, finding any information about means information leakage about XI is XI information leakage is very less here because TIs are independently generated. TIs are independently generated. Okay, so you can there are several other modes. This combinations counter mode plus CBC mode. So counter with cipher blockchaining mode, you can get counter CBC mode. I can't remember what I wrote here. It's not scanned properly. Okay, so this is. So block cipher, we have covered block cipher and different modes of operations also we have completed. Now let me introduce, let us introduce stream cipher. Okay, and another thing I want to I want you to think what are the advantages. You think what are the advantages of these different modes? What are the advantages of counter mode over CFB mode or CFB mode and OFB mode? What are the advantages? Each of these mode have their own advantages and disadvantages. And another point, how to choose this IV? If you every time if you choose the same IV, what problem you are going to face? Think about that. Okay, so these things you have to think. If this IV should be chosen randomly every time, or it should be fixed always. If it is fixed always, what type of problem we may face? Okay, or randomly, if you generate, how to generate this IP randomly? Those things, you think about those things. Okay. Okay, let us stop here. So in the next class, we are going to learn stream cipher.